Welcome back to the contribution of this session. I think that the coverage basically signed up we can start. Announce and change the program because unfortunately the first scheduled speaker, that was Professor Natalia Kizio, is absent. And then the first speaker will be Professor Fainleib from the Department of Heterochain Polymers and Interpretable Polymer Networks with the Institute of Nanomaterials Chemistry. That he will report on hybrid polymer networks, but anyways also author and co-author of many other contributions to the report.
Just a minute. Just 1 minute.
Okay, then please hear from one of the systems.
I'm here.
Bisphenol E, designated step of bisphenol A, C
solve this problem, the scientists usually modify them by some inclusions of elastic modifiers. They used usually copolymerization of these designators as bisphenols with reactive monomers, oligomers, polymers, which are elastic in nature. And the other way is to prepare so-called semi-interpenetrating polymer networks, which consist of the polymer network, this rigid polymer network, and elastic linear polymer. But all these modifications improve the mechanical characteristics, but on the account of some reduction in thermal stability. And the new way to modify these networks to improve physical mechanical characteristics without any loss in thermal stability is the synthesis of the nanocomposites. So the hybrid nanocomposites based on polysaccharides and reactive silicon-containing nanoparticles were prepared this fall, and we used a wide range of the concentration of the nanofibers, starting from 0.01 weight percent to 10 weight percent of 3D epoxy pores or 2D amide compound. And there is a chemical reaction during the network formation. The nanoparticles of pores of 1 nanosize nanometers are incorporated chemically inside the polymer network. So it's improved the dispersing of the nanoparticles due to chemical graphing inside the polymer matrix of each nanoparticle of 1 nanometer size. And similarly, we have the process for obtaining amide monomeramide field nanocomposites, polysaccharide based nanocomposites. Just a different reaction, but it's a reaction of amine groups of monomeramide with cyanide groups of growing polysaccharide network. And finally, we have a similar structure, and usually organic polymer network has organic junctions in the network, but in this kind of materials we have, along with organic junctions, also the inorganic junctions, like the particles of pores or particles of monomer due to chemical grafting. Here we can see the methods we used to characterize and obtain nanocomposites. It's TEM, SATS, EDS, FGR spectroscopy, also far-infrared spectroscopy. The CDMA is traditional methods for characterization of polymer materials, and quite specific laser interferometry free-grade spectroscopy. So the next slides will show the results of the. So here we have TEM photos of the PCM pores nanocomposite structure. And we can say that the structure of 0.025% nanocomposite is very similar to the pure polysaccharide network. It confirms the very good dispersing of this ultra-low amount of the nanofiber inside the polymer matrix. And then when we increase the amount of the nanofiber, 1%, 2%, we have some formations
we can say that the concentration of silica atoms is quite high in the dark zone, conforming the formation of the aggregates in this case. And here we have local silica content versus pore concentration ratios. And the dashed line corresponds to the calculated ratios as expected for uniform pore distribution. And the experimental line shows the experimental result. So you can see that at the beginning, at low content of the nanofigure, it is very close, the experimental results to the calculated ones, as for the uniform distribution of the nanofigure. And the higher content of the pore nanofigure, we have more negative deviation from the theoretically calculated ones. So it confirms that the distribution in this case is not so good, and we have aggregates from formation in this case. And here we have the histograms of local silica distribution in PCM pulse number composite, characterizing the homogeneity and heterogeneity of the distribution within the market. And dashed lines give us the average silica content. So it's for 0.5 and for 2% of course we have quite narrow distributions, good dispersion, and wide distribution for higher content of pores in the system. So for 5% and for 10% standard. And we were not able to have figures for ultra low amounts because the spectral signal is on the level of the noise. But we can imagine that the most narrow distribution, the best dispersing, it will be fixed for the ultra low amounts, so much lower than 1% of the figure. And also this results confirm formation of aggregates for high content like 10% of the nanofigure. And here we have the TM photos for net polysaccharide matrix. Then it is for 5% monomerilonide composite, which show us the multi-layer monomerilonide aggregates in DCB matrix, polymer matrix. Then for 2%, we have stacks of 10-15 nanolayers in thickness. For 1%, we have 5-7 nanolayers in thickness. And for the best sample with 0.025% composite, we have a single monomerilonide nanolayer. And when we compare also the dark and surrounding zones by infrared spectrum. So these results show suggest the quasi-periodical distribution of force starting from the just very small amount of force, 0.025%. And far infrared spectra also have shown some changes in the spectra for nanofields with different amount of nanoparticles for nanocomposites. And we have a fixed suppression of triazine cycles vibrations in this zone. You see the difference. And also the changing of character of torsional skeletal vibrations for the nanocomposites with small amount of force in this region. And very interesting results we have got with the determination of glass transition temperature for nanocomposites in different amount of nanofields. And we can say that we have fixed the increase in glass transition temperature for the nanocomposites with ultra low amount of the nanofield. So you see when we increase, when we add some small amount of the nanofield, in both cases, both and non-polymer, we have increasing glass transition temperature. This increasing is around 40-50 degrees centigrade. And then when we increase more the content of the nanofilter, we have decreasing glass temperature up to the value equal to the unsealed polymer network and even lower. But this is due to aggregation. So we have good results for samples with very good dispersion. And also polyaccelerate nanocomposites were studied by laser infravertical deep-range spectroscopy. And we fixed the impact of low-cost additive on polyaccelerate constraint dynamics. They pronounce dynamic heterogeneity around the glass transition and enhance the high-temperature creep resistance. So the layer consists in decreasing creep rates and increasing the temperature of the sharp creep acceleration fraction sample from 260 for net polyaccelerate to 330 for the nanocomposite. It's 70 degrees increase, very good effect. And with similar effects we have got with nanocomposites based on different polyaccelerate markers. It's like DCBA or polymer T30. We change the original basic structure of the polymer markers and use the same fillers and amount of fillers, and got also the increasing glass transition temperature and then decreasing depending on the amount. And here we have checked the behavior of the nanocomposites after some thermal treatment close to the glass transition temperature. And we found that here, this is the changing of glass transition temperature with the temperature treatment for network, and this is for the nanocomposites with 0.01, 0.25%. We have enhanced resistance to thermal degradation to nanocomposites with ultra low cost content. And in conclusion, if you see a thermostable nanocomposites with different density cost of the amount of was studied, and the basic result Слава Україні!
Thank you, Professor Fainleib, for this interesting comprehensive report that was also very almost here. Our paper is open for discussion. Please, question? Your is any question? Yes, one.
Can you change the size of silica particles in glass panel?
We can use any
What
size.
is the range?
We checked from 0.01% to 10%.
Only size of particles, no concentration.
Size. It depends on the particles we use, because we didn't produce nanoparticles.
Can you receive approximately 10 nanometers or 20 nanometers?
No, even 100.